Okay, so a couple things. I listened to some of the lectures from last week, and the sound quality is good enough. Okay, it's acceptable. So I uploaded the two lectures from last week up to YouTube and created a playlist for this class. And then I put the links for each video in Canvas. So if you need to go back and review something that we talked about, um, you have that capability. I don't know how um, efficient I'll be at putting everything online, right? So ideally, at the end of each day, I'll have each day's lecture up and available for you. I will not promise that I'm that organized, but we'll give that a shot. The schedule, right? So today we're going to talk about, or this week we're going to talk about agent-based systems, and then next week, we're going to go into some basic statistics stuff. Next Monday, we have off because it is Memorial Day. So agent-based systems, and I might spend a little bit more time on experiment design. We'll see how it goes. It may be hard for me to talk for, gosh, what is it, 4.5 hours on agent-based systems. But each day, remember, I want to reserve some time for having some working time. So um, let's see. Alex had sent me, had posted a draft of her deliverable for tonight. I was able to give her comments. William, you also posted a draft, is that right? And I gave you comments and sent comments back to you. So I'd like to talk to y'all if y'all have anything at all, even just notional ideas about what you want to do. How do you present it? If you have a draft, that's even better, and we can look over it. Even though you won't get into the meat of your research until you do the background, you should have some idea of what you're doing, which means you should already have a couple of papers, already in your reference blocks, and then citing them in this section. It doesn't mean you have to go into a lot of detail about what's happening. It just means that if you make a claim, then you put a reference in. One of the things that I have trouble with undergrads and some grads is they don't understand the degree to which you have to use citations. So literally every time you make a claim, you either have to prove that claim within the body of your paper, or you have to have a citation, a legitimate one, not some clown on the web, but a legitimate citation, where I can go and look and, oh yeah, they really did say that. Which means if you think about what they taught you in English Composition 1, every sentence is a statement. Every statement is a claim, which means almost every statement, almost every sentence, you may end up with a citation. And I've seen papers and I've written papers like that. That's not to say that every paper is like that. But if you're saying there's a claim, here's a claim, here's a claim, here's a claim, well, they better have a citation, 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 citation. There does get to be some style issues where if you make three claims from the same paper, can you put one marking at the end? I like to oversight, because if there's three claims and there's one at the end, I don't know if all three are supposed to go to that one. It's ambiguous, right? I don't know if all three are supposed to go to that one or not. So you have to use your judgment at that point, standpoint. Okay. Anyway, the bottom line, I want to work with you a lot in class. Again, the challenge with this particular class, doing it in 6 weeks, is trying to pull together a good research, a good simulation, and get some good results in a really short calendar time period, which means I'll try to help you along the way here. All right, so let's see, where the heck am I? So in agent-based systems, I have a bunch of papers listed. Where are we at? All of these PO1, PO2, PO3, a bunch of papers listed. The one that's listed, C350 P11, paper 11, Bonobo, is like the best agent-based paper ever. If you only read one of these papers, read that one. That's a great summary. And it's a little dated, but things haven't changed much in terms of how we can categorize things. So I'm not going to go through the paper here, but that's what it looks like, agent-based methods and techniques for simulated human systems. And the author there does go through like I said, just a really nice menu of here's how you can do these things, and here's how we can categorize the kinds of agents that we're dealing with. It's good to have language like that, right? Where you don't just talk about an agent. Remember the what was an agent again? What did I say an agent was in a simulation or in a system?
Something that decides?
Yeah, it's a decision maker, right? That's a pretty broad field, right? So then you get into, okay, are they purely reactive, meaning they make a decision in the moment based on the immediate situation with no other factors? Do they maintain a history? Do they change their decision making based on their history? Do they plan ahead? Do they interact with other agents directly through communication, or is it indirectly through observation, or not at all? So there's different ways that we'll discuss how you can categorize these things as we go through the week. All right, so same trick as before. I've got just a bunch of definitions, and we can walk through the definitions. So again, an agent is a decision maker. And I put the word distinct in there so that we can try to classify, okay, it's an entity that you can define the boundaries on, right? That's what distinct means. We have typos. Yeah. So agent-based simulation or agent-based systems, the agent is the thing. And the thing that makes the system work is not so much generally I'm speaking, not so much the decision of the agent in and of itself. It's generally, we get really interesting systems through the interaction of different agents. So if an agent makes a decision, that's great. But if an agent makes a decision that affects how another agent makes a decision, which then in turn reflects back and affects how the initial agent makes the next decision, now we've got interaction between the two. And once you have interaction between multiple agents, that's when things get really interesting because we tend to be talking about systems that are hard to model and they can be hard to predict. So if you think again of where can we go? I was talking for some reason, my wife and I got onto the beginning of World War I. How did World War I start? So simplified form, it was basically a very complicated set of interlocking agents with the interlocking agreements, right? The different nation states being the agents. They had a whole complex set of mutual treaties that overlapped, and basically it was all trigger behavior. Once one event happened, then someone said, I will honor the treaty, and this will happen, and this will happen, and this will happen. But it all happened because of this interaction between the nation states, the agents. And none of them predicted what would happen. It was what we call emergent behavior that was based on the interaction between the nations. And none of them predicted how horrible the next 4 years would be. Everybody's like, oh, we'll be home by Christmas right there. Everyone's going to be home by Christmas. So the agent is the decision maker, but the interactions are the things that tend to, and I'm saying tend to make these things really interesting. Now, you could have a simulation with a single agent and the agent is doing something. That's okay. That's normal. That is where we'll tend to get to like in the robotics club, they may do some simulations to try to develop learned behaviors for a robot to operate in the real world with. You put it in a simulated environment, and then you let it crash and burn in the simulated environment over and over and over again, and then it will. And if it's a machine, if you employ machine learning, it will learn, and then you take those learned rules, put them in a machine in the real environment, and hopefully it does well. By the way, that's a whole nother issue of transferring learning from the training environment to the operational environment. That's a whole nother issue. But notice that robot, or that simulated robot, is an agent. It is making decisions, but it's not doing interactions. So you can have systems like that where you have agents that don't have the interaction, and the interaction is not the critical part. However, those kinds of simulations tend to be not as interesting in the sense that you can more or less prescribe the boundaries of the behavior of that agent pretty well and have a pretty good idea that you're right. But when you have the agents interacting and the behavior of the large-scale system is based on all of these interactions, it turns out that's really difficult to predict. It's difficult to predict in the real world. It's difficult then to model. It's difficult to understand what's going to happen. And therefore, these simulations are of more interest to a lot of people because since we can't model, since we do have real world behavior that we're interested in, but we can't model it, we're going to run some simulations, and it's basically, let's just see what happens. Right? Here's some initial conditions, here's some boundary behaviors, let's just see what happens. Is the stock market going to crash? Well, the stock market is thousands and thousands and thousands of agents all interacting with each other. All right. So what is this notion of an interaction? I'm defining it as stimulus response pairing. One agent's actions directly or indirectly influence the actions taken by another agent. So, agent-based system. Somebody in wherever they do this stuff scheduled us for 9 o'clock for this room. That was one agent's decision. And then it's our response as agents was to show up here every day at 9 o'clock. I agree. Like I'm not even awake yet, right? So that's a notion of an indirect interaction. You didn't interact directly with the agent that scheduled this class. They kind of left you a token, right? They left you some information and you picked up the information. And so you had an indirect interaction as opposed to what's happening right now. I'm talking and you're choosing to listen or not listen, or you're responding to what I'm saying. These are direct interactions. We also have other direct interactions, though. One direct interaction is, I don't know, pick me a random number between 1 and 10. 7. There we go. That's a direct interaction because I gave him an explicit request and he gave me information as a response to that explicit request. But we could have other forms of action that are still direct interactions, but they're not direct communications. And we do this as humans all the time. I cannot emphasize how much we do this as social creatures all the time. Have you ever looked at somebody and you're like, that person doesn't look quite right. I'm going to take a different aisle down the grocery store, just in case. That's a form of an interaction. But notice it's indirect in the sense that there was no explicit communication made between you, but there's still observations. So we have situations like that. You've been driving down the highway. This happened. I'm driving down the highway today, and I see brake lights ahead, and I'm like, uh-oh, my response, or uh-oh, I hope there's not going to be a problem, right? I hope we're not going to get all snarled up in traffic. No, we didn't. But you're immediately responding to what you observe. There was no, I guess there was there because brake lights come on, right? So there's some positive form of communication. But what you're watching is just the behavior of another agent without that agent explicitly communicating with you. So there's different layers of communication that we can start to talk about. So when you define agents, spirit with you, when you define an agent, we're going to define how do they communicate, and as well as their internal state. How do they plan? Do they not plan? That kind of thing. Yeah.
I'm just going to say, the whole reason for brake lights is they took that indirect action and changed the direction.
That's a good point. Yeah, the idea of a brake light is it turned the indirect action to a direct action. Let me try a better example of driving with an indirect. I've been down the road sometime and the car immediately will swerve out of the way of something and then come back. And I'm like, okay, now I'm prepared. There must be something in the road that made them do that. And when I get there, I'll see it and you know, but I've already been prepared. They did not intentionally communicate anything to me, but I can watch their behavior. You see this with vultures too, right? If one vulture starts circling, the other one starts showing up like, hey, maybe that guy's onto something. So you see this with different agents, right, in the real world. So two main effects of this, right? Simple agents can produce complex behavior as a result of their interactions, and then the nature of the complex is difficult or really, really difficult to predict. And like I've said, I've found a couple of you can find places where people publish, okay, here's how we're going to try to model a system of agents, and it's always this ungodly, horrific matrix of junk, right? It's just really difficult to pull off. So what do I mean by simple agents can produce complex behavior? I mentioned ant logic the other day. Ants in and of themselves are pretty limited in what they can do, a single ant. And they're quite fragile. An ant colony is quite robust. It's easy to kill a single ant, difficult to kill an ant colony. A single ant can drown. An ant colony basically doesn't drown. They come through wet weather okay. They achieve a lot of their success through interactions, and their interactions tend to be through like pheromone dropping, right? So it's kind of an indirect, I'll drop a pheromone and then another ant will come along and pick up that scent. But they tend to do that. They're not, I believe the consensus is they don't have free will, right? They're kind of just triggered by chemicals. If the ants colony, if enough of them are producing the scent that says, I need food, that will trigger some ants to go out and search for food. Once they find food, they will trigger a found food scent, come back to the nest. And you've seen the trails of ants, right? Going from one place up to a dead grasshopper or something like that, right? They're dropping scent along the way. And not only will they find food and then through the scent trail lead other ants to that piece of food, over time, they will find an optimal or a near optimal route to get from the nest to the food and back again. So if there's a big loop along the way, over time, they'll get rid of that loop because one ant will kind of go nuts and go off track and just by random chance shorten the loop a little bit. But now once it's shortened the loop, that scent trail will become stronger quicker over time than the longer loop because the scent fades over time. And so they will start to optimize their path. We take advantage of that in computer science. We have a problem called traveling salesman. Traveling salesman is a path-finding problem where you're trying to find efficient paths. And one of the ways to try to solve it is to release a bunch of agents on it. It's called ant logic. Release a bunch of agents on it that are randomly going through different parts of the path and tracking what's optimal and what's efficient and what's not. And as you start to piece together the results, you will come up with eventually a optimal path through the graph. So they can produce simple stuff. The problem here is, again, the complex behaviors that you're getting are difficult. Now, some things are on the border between what's a complex or a better behavior that's not just an aggregate behavior. For example, a single ant may not be able to lift a bug and bring the carcass back to the nest, but 3 or 4 ants may lift it together and bring it back to the nest. Now, is that just aggregate behavior, like combining their strength, or is that an actually emergent behavior where they're doing something new that they couldn't do before? And we could probably argue for a while if we wanted to about that, right? So what the difference here with this emergent behavior that's different from aggregate behavior is exactly that, right? If the lifting of the carcass is a good example of aggregate behavior. Or if you have a team of horses pulling a plow or pulling a heavy object and you need more power, what do? You get more horses, right? That you're aggregating the strength of the horses, right? And there's a lot of things that behave in an aggregate way. You've done these problems. If a person can dig a hole in an hour and then you have three people digging a hole, how long does it take? You know, that kind of thing, right? You've done those in SAT, probably had questions like that. And the idea is, oh, that's just aggregating behavior. If one person can dig 5 holes in 10 minutes, how many holes can 6 people dig in 20 minutes? You know, that kind of question. You're just aggregating the behavior. As opposed to the emergent behavior. Notice in the example problem of digging holes, everybody was still digging holes. There was no new meta-level behavior that showed up. As opposed to the ant colony, which is saying, look, as a single ant, I can warm my body and cool my body. Now I can use that entire thing as an emergent an emergent behavior to warm and cool the entire nest. Being able to warm and cool a nest is not something ants can do, right? An individual ant can do, but as a group through emergent behavior, they can. And what's the emergent behavior? Some of them are giving off the, oh, I sense that we need more heat in the nursery. Others of them will pick up that scent and volunteer. They have different like trigger set points, right? Volunteer to go get warmed up and bring their bodies back down and carrying the heat into the nursery. The weird thing about these, again, simple creatures is that through this interaction and emergent behavior, they can do complex things. An ant colony in the rainforest, army ants, they bivouac, as they claim, and then they move around, right? So they're constantly moving. Why are they constantly moving? Because if they stayed in the same place, they would eat all the food supply and then they would starve to death. So what do? Their behavior, which has been evolved over time, right, is they stay in one place for a while. When the food supply gets low, they move to a new location. And then when the food supply gets low, they move to a new location. But they tend to do it in a pattern where they're basically making a big circle and they'll eventually come back to where they were. If they come back too early, the food supply won't have refurbished. So they have a big circle that's big enough that they're getting new food everywhere they go, staying within the same basic region, and able to not deplete the food sources within that entire circle. It's a pretty complex behavior. You've seen videos of them crossing streams where they make bridges of their own bodies. This is a behavior that an emergent behavior that the hive can do, right? The colony can do, a single ant can't do. Yeah.
I was just wondering if you were just like really interested in ants, or you had to learn about this.
Oh yeah, through time, because so many examples come up with this, and people use this as models, and then they try to figure out how can we use this, because we have now, you know, UAVs and non-embodied agents, right? So yeah, and the whole point with ants is because it's a really rich field to try to study interactions. When they're not studying ants, they study bees. No. It's just that's where a lot of the research goes. And you can look up ant logic and you'll find paper after paper after paper after paper. The reason is there was a biologist called O.E. Wilson, and he made certain claims about certain species of animals. And he said some animals are social. But some animals, and I forget the word, I think he called it eusocial, which is like super duper social. And these animals, which are super social, are showing traits that other species don't. And he puts ants in there and bees in there and us in there. And he's saying one of the reasons we took over the world is because of this super social behavior that we have. Yeah. So people study ants a lot. They study bees a lot. Dr. Watson in our department is a systems engineer, And he's doing some work with grad students about how can you detect infected computer systems by stealing the techniques that ants use to detect infected ants. Because if there's an infected ant, they got to get it out of the nest immediately before it kills the nest. So they're studying that. But he's also studying how can you get consensus among a bunch of software agents by using the same technique that causes all the sea turtle eggs to hatch at the same time. See, so there's people go to nature and look at something and say, I wonder if I can use that. I wonder if there's a way I can model that and use that. How do turtle eggs hatch at the same time? I don't know.
When you start making it, what they do is they start slowly, it's just like how, like, if we all start playing music, start tapping on the desk.
Right. Right.
With each other. It's just, they start doing it like that, and then they start cracking the eggs at the same time.
So they have agents that are all contained within their own individual shells, but doing interactions via the tapping. And through the tapping, they create the emergent behavior of being released at effectively the same time. But they are agents, right?
Well, it's a two-step process. First, it's they beep. They
Okay.
make noises. And so you can model that as having a plus or minus value for each agent.
Right.
So it'll either move it left or move it right in its time frame of when it beeps.
Okay.
And that gets closer and closer until they're all aligned with each other. And then once they're all sounding together, then they start tapping.
Oh, okay. So they vocalize first, and that's an interaction. And once they are able to kind of come to an agreement through the vocalization, then what? Do they start tapping just to tap, or are they starting to break the shell then too?
From my understanding, I mean, it's not like they just pop the shell.
Yeah, right. Okay.
Process.
Okay. So the point is people are looking to natural agent-based systems to try to figure that out. So thank you for adding that, because that's good to know. That's kind of neat. And I'm going to throw in as opposed to, so a chicken or a goose, like a chicken, as you know, will lay an egg if they're very productive, basically once a day, as long as there's enough sunlight hours in the day. So they lay it once a day. And then once they get to, like, whatever number they choose, 10, 12, whatever, it's not like they're thinking about it. It's more of I think it's more of a hormone thing. Once they get a good clutch of eggs, they'll stop laying eggs, and then they'll start sitting on the eggs, and then the eggs again hatch at the same time. And the chickens, once they start sitting, it takes 25 days for the egg to come out. But some of those eggs are like 25 days old. Some of those eggs are like almost 40 days old because they've been laid over time until the hen sits. Well, what the heck? How are they still hatching at the same time? This is not, I believe, not agent-based behavior. What's happening there is the egg, when it's first laid, kind of just goes into stasis, and it's not until the sitting happens that triggers the egg to start to develop. And then they all start to develop. So now they've all developed basically at a 25-day period, because the older eggs kind of pause their development until I believe I suspect it's the heat of the body of the hen that makes it go. And I only know this because, we used to have chickens, and that's how they worked. It's not about inside the egg, the little chicks encouraging the other ones. Now, maybe the day that they hatch, maybe they do. But in terms of the overall development, it's not. The sea turtle eggs are a little different because they're all laid on the same night and then developing the same period of time. So the interaction for them makes a little more sense. Plus, there's no mom around. Okay, so really difficult to predict or bound this stuff. And some of these you can, right? We may be able to model the turtle egg behavior and have some pretty good predictions about what's going to happen. It's a lot harder to model how different groups of people respond to events, or how different groups of people are going to respond to how one person or one group of people performed an action. Those are a lot more difficult. Aggregate behavior is more simplistic form of pulling behavior together. So if you say, oh, like a GoFundMe is an aggregate system, right? If you put in 10 bucks and you put in 10 bucks and you put in 10 bucks, right? We all put in 10 bucks. We've got 1, 2, 3, 4, 5, 6, 60 bucks in there, right? It just aggregates the results. That's different from the emergent behavior where we get a new capability or a new behavior.
Well, unless like 60 updates, you
Yeah, it passes some threshold or but the collection of the money basically didn't change, right? If we can get more people, we get more money in the thing. So with my example, the total number of meals sold at a restaurant, it's just the sum of the individual meals, right? It's an aggregate. If you are tallying up your sales at the end of the night, right? It's, we sold this many, this many, this many, this many. Okay, that's how much we sold of everything. That's how much money we have. It's just adding things up. Again, as opposed to, say, the ants crossing a stream. There's no way an individual ant could get across the little stream, but the colony can. So it's a new behavior. Okay, we've talked about. So ant and bee colonies, super common. However, people do start to look at, I told you about last week about Bill Tomlinson was his name at MIT for his PhD thesis. He looked at establishing dominance hierarchies within agents. So instead of just having agents that, okay, so here's the background of that. One way that people do agent-based systems, and they're going to do task allocation, or then in his case, he was doing like we were doing like an opera problem thing, but basically doing task allocation is you can have the agents basically hold an auction with each other. Or if you want to get a resource, you want to gain access to a resource, you can have the agents hold an auction with each other. And so they're going to hold this auction and one of them will win. What he did, and then the next time you need that same resource, you hold another auction. It's not a bad solution. However, can you think of any reason why people don't really love this system? Yeah, it takes a lot, it's a lot of work. And in terms of computation cycles, right, it's a lot of extra effort to get something done. So what he did as an efficiency measure is he started to impose a dominance hierarchy. So if we're holding an auction for who can get out the door, and Joe bids higher than me in the get out the door auction, the next time we need to bid on who gets out the door, if I see Joe's in the running, I'm not even going to participate because I'm like, well, he beat me last time, he's going to beat me this time. So what we're doing is establishing through history a hierarchy of who gets priority. And that is going to be more efficient. So ants and bees are studied a lot, but he was studying this dominance hierarchy, and I mentioned this last week, and he called it the project he worked on, he called it Alpha Wolf, and it's based on the wolf dominant structure within inside a pack, which you're pointing out was done for captured, not in the wild behavior. So even though ants and bees, again, you'll find a million ants and bees. People look everywhere in different social structures to see if there's a way that we can use that behavior. Let me take a quick side trip about that. This whole thing is about, a lot of this is about, can we come up with developing behaviors for autonomous agents, because autonomous agents are becoming so prevalent in our real world. We need our autonomous agents to behave well, behave nicely with each other, to be efficient in their operation. Some of this stuff is just trying to study behaviors of complex systems. How do you prevent crowd panic in a situation that may cause panic? We've all had experienced reading over time situations where there's a really crowded nightclub and a fire breaks out and a bunch of people died. And some of them died because of smoke inhalation, that kind of thing. But some of them died because they got trampled to death. Or more people died because there was so much panic that they couldn't get out because they were, blocking doorways and things like that. Some people are studying, can I actually design a building in such a way that in a panic situation, the architecture, the shape of the internal space of the building actually promotes people getting out safely as opposed to restricting. So people study these kinds of things not only to figure out how can we make efficient software agents in the real world, because that's becoming more and more of a real thing where we have software agents in the real world, but also just how can we, just other systems. How can we find ways to reduce panic in buildings? How can we find ways to understand how the stock market's going to work? How can we find ways to understand how political violence occurs? All of these things are agent-based systems. Sometimes we're the agent, the human is the agent. Sometimes there's software agents. A lot of people, as you would expect now, are assuming that the sky is going to be filled with UAVs shortly, and they need to play nice. They can't just be running it into each other. You can't have a UPS killer drone hunting the Amazon drones, right? That would not go over well. So people are studying like crazy. How can we develop good rules for how UAVs interact with each other, or how in a mixed airspace with piloted and non-piloted vehicles, how can we share that space? Same is happening on the roadway. Driverless cars and drivered cars. Cars with drivers and driverless cars. How do they share the roadway? Right. So these things are being studied a lot. And again, people are going back to existing social systems, animal or human animal or other animal. All right. I've been talking a lot. Questions? Okay. Initial conditions. I think most of us are familiar with this term, but let's give it a nice good meaning, right? So they are the state of the simulation at the beginning. So when I talk about you're going to run a simulation and you need to do experiment design and you need to run some experiments, what we're really talking about with experiment design tends to be establishing what the initial conditions are. I've got 4 variables, and what we'll talk about later on when we talk about experiment design. I've got 4 variables. I'm going to artificially label some value for each one is high and some value for each one is low. And then my initial conditions might be low, 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 low for all 4 variables, that kind of thing. The kinds of simulations that you'll be doing in this class tend to be where there's not human interaction. Once you hit go and it starts to run, it tends to be where there's not human interaction. So the initial conditions are going to establish everything after that. Now, having said that, once you set up the initial conditions and you start this thing moving, you start the simulation progressing, because you have agents in there and because agents are decision makers, and generally you're going to create agents that are not fully deterministic in their decision making, meaning there's going to be some randomness in there. That means you can start out with the same initial conditions and run your simulation 2 times and get different results. What's the implication of that? You generally can't run a simulation once and say, here's a result in that case. And generally what you have to do is run it 100 times and then average the results or somehow combine the results. Which means when you're designing these things, it's not a bad idea to design them where you set up the initial conditions, but then you also say, okay, now run this thing X times, right? Where you put in, here's how many times I want you to run. That's the best way to get to run experiment design, or I should say the best way to develop your simulations. That doesn't mean we'll pull it off this semester, but that's a goal for you. Anytime you can automate anything, right? You don't want to sit there and restart your simulation 100 times by hand, right? If you can make it just go. Okay. One of the reasons I even bring this up, though, initial conditions, I think, is a fairly well understood concept. You've heard of, oh my gosh, I'm old. You've heard of chaotic systems or mathematics chaos. Is that true? Okay. By the way, I was going to use the original Jurassic Park as a reference, but I think that came out in what, 93? 95? Way before you. Have you seen the movie? Classic movie. Remember the scene where he's dropping water on the woman's hand, and sometimes the water droplet goes one way, sometimes the water droplet goes the other way, and he's like, oh, that's chaos theory in action. That's basically true. The idea behind the initial conditions is that emergent systems tend to be, I should say, can be chaotic. And they can be chaotic in the sense that they're extremely sensitive to small changes in initial condition. And if you have a system that's extremely sensitive to small changes in initial condition, it's actually a pretty good case for making an agent-based simulation out of it. I talked about game of life the other day. I didn't talk about Boyd's. Let me try to really quick pull this up. Let's see, I didn't do my prep work. I have no idea. There used to be great Boyd's examples out there, and then they disappear somehow, and there we go. Let's see what this does. Oh, there we go. It's going fast. Boyd's is used as this is an old, I don't know how old, 20 years old or something like that, this notion. But the idea is it's a flocking behavior algorithm. And you get flocking behavior. As you can see, these entities are doing good flocking now. When it started, they were chaotic. They were all random. And then they started to form into small clusters, and eventually they form into one flock. Now, they didn't do it because anybody's in charge. There's no king or queen in there telling everybody what to do. They're doing this just based on interaction. It's all agent-based interaction. And there's three basic rules. This one's doing, this one's put a fourth rule. So there's three rules: coherence, separation, alignment, and then visual range. So what's happening is each one of those, at each time step, this is a time step simulation, at each time step, they're going within their visual range, and they're making a circle. And for every other Boyd within their visual range, they are checking the alignment. So they'll average the direction that all the neighbors are going, and then they'll use that as part of a vector. Separation, they want to make sure not to run into anybody, so that makes another little vector. Coherence, they want to go to the center of mass of their local group. And so that makes another little vector, and they add those three little vectors together to get a resulting vector, and they move a little bit in that time step forward in that direction. And by doing just those three stupid simple rules, you get flocking behavior. Now, again, this has been around for a while. It's pretty cool. There used to be one that had a predator, and the predator would break up the flock so you could see it reform over and over again. There's also versions, I don't know if this one has it, there's versions that you can build different tribes. You were talking about tribes the other day, different colors, and they'll only flock within their color. Very racist, but you know. So there's different versions of this stuff out there. Like I said, it's been there a while. Now, I could walk it for hours. It's kind of cool. But why do people care? Well, one, it's just a really great, see, we start with that. It's amazing how quick it will come together. Maybe. So I show this because it's a really good example of emergent behavior. It's a really good example of how you can get really neat looking behavior out of simple, again, stupid, simple rules. To the degree that You seen Lord of the Rings? No? You seen Troy? Horrible movie. These movies nowadays where they have thousands and thousands of orcs or soldiers or whatever, they're kind of using a highly evolved version of Boyd's. Because let's face it, when they have all those groups of people yelling, digitally created groups of people or animals running along in a group, it's this behavior. Now, I said it's not quite this behavior because they did do apparently learning algorithms over time to get the right behaviors that they wanted, but basically that. So simple stuff. You can play around with, if you make this, play around with what's important. If you make it where they can't see very much, I would think you would get a lot more spread there. Anyway, by all means, you can look that stuff up and play around with it. Okay, game of life. See if I can find that real quick. So let's see, do we have rules? Somewhere in there's rules. So this is, again, it's just cells, and the rules are going to be basically if I'm lit up, I'm alive, and if I'm lit up all by myself, I die. If I have, I think I think if I have 3 neighbors and I'm dead, I become alive. If I have more than that, like this, I think stays dead. So basically, there's really simple rules about whether you light up or not. And it's called the game of life because I don't know why I call it live and dead. So, stupid simple rules. But you can get complex behavior out of this. And people have proven that this simple system, no one's done it to my knowledge because it would be so annoying, but people have proven that this simple system is completely Turing computable, meaning this thing can compute anything that your computer can compute. I don't know how you would represent data. Sounds awful. So people have developed patterns, and if you notice, this is a repeating pattern. So people have developed these patterns, and this thing will go on forever. I think it'll go off the screen, but you can resize these things. Oh, stop. Oh, that's next is that. Let's see, there should be, do we see a, here we go, let's see here. Oh, found in 1994. Let's see what this does. I don't know what these are. Yeah. That's the one I want right there, the gun. Can I do it? Okay. Okay, so if you see what's happening here, this is a factory. And it's producing these sliders, and they go off down the screen here. But this factory will keep producing them forever. Now, again, not an obvious thing. Who would predict this stuff? This is emergent behavior that is very difficult to predict. And that's why people, you saw in the text there, this pattern was discovered in 1994. So it's been around a while. But the idea is it's so complex that people are playing around with this. One version of this is how do you try to fill the whole screen out or cover as much of the screen as you can, that kind of thing. Notice, by the way, these guys are stable because I think if you have 3 next to you, you stay alive. If you have more than three, you die. And if you have, in order to create one, you need to have three. So notice that guy went away for a second. You're gonna go, he goes away, but then he comes back. So these are just examples of agent-based systems, and they're, in a sense, toy examples, but they're also meaningful because they describe what's happening, first of all. They give you a sense of, oh gosh, that's what interaction looks like, and I do get weird behaviors, you know. That idea that you can create these patterns that self-replicate, or you can create patterns that are for eternally creating new patterns, is a behavior that an individual square cannot do. Right? That's a high-level system behavior that an individual square can't do. So it's a true emergent behavior. Okay. That's I think that's what we need for. Let me walk through this. This is pretty short, and then and then I want to talk to you about your have working session. Okay. All right. So when is it good to use emergent behavior? Or when, I'm sorry, when is it good to use agents? When the emergent behavior is present. What does that mean? This is out of that Bonobo paper, by the way. Individual behavior is nonlinear and or discontinuous. Individual behavior exhibits memory dependencies, learning, or adaptation. Individual behavior is heterogeneous. Individual differences are amplified, not averaged out when predicting system behavior. It's this last one. I want to talk about this for just a second. This one is in my mind, an easy one to grasp. Think about it this way. Let's say you've got a bunch of vehicles not on a road, just vehicles, I don't know, ships out in space. And you've got 10 of them, and they're all going 1,000 miles an hour. What's the average speed? 1,000 miles an hour, right? One of them breaks down and stops. Oh, it's in space. It still stops. Now you've got one of them at 0 and 9 of them at 1,000 miles an hour. What's the average speed? Well, now you're looking at what, 900 miles an hour, roughly. Okay? That's aggregate behavior. Now, instead of spaceships out in space or boats in the ocean or whatever, let's put cars on a single lane road. I've got 10 cars on a single lane road, all going 40 miles an hour, one after the other down the road. What's the average speed? 40 miles an hour. The first one breaks down and blocks the road. Oh, the whole system's screwed over now because everybody has to stop. So what's happening here is when you have an individual behavior can radically affect the entire system, that's a good case for agent-based systems. And that's when you know that you're dealing with a system where emergent behavior is going to be more important than the individual behavior. Individual behavior is heterogeneous. What does that mean? The big argument here, but you can get into these big arguments when you're designing a system about homogeneous or heterogeneous behavior. So heterogeneous just means different, right? That's what that means. So we have different behaviors in the agents. There's so for example, where would this come into play? The Naval Research Lab 20 years ago did some experiments with machine learning. And the machine learning were basic, stupid, simple agent operations. Are you aware of like how sheepdog trials work? There's generally 3 sheep, and you have a sheepdog, and the dog goes out, and the guy who owns the dog has got a whistle, and they're whistling and giving the dog commands. And the idea is the dog has to take the 3 sheep and run them through a circuit and then put them in a pen. Okay. And a lot of the decision making, quite frankly, is done by the dog. The dog and the guy controlling the dog act as a team. And if the guy controlling the dog sees the dog is doing a good thing, he shuts up and lets the dog do a good thing. So, and they're border collies, so they're not dumb. So, the idea here was they did an experiment where they put in agents that were sheep, and the sheep were just, think of circles on a screen. And then they put in an agent that was a dog, a sheepdog. And the only real behavior the sheep had is if the sheepdog came close, they would run away from the sheepdog. That's all, basically the only behavior they had. And the behavior that the dog had initially was dumb, stupid, I'm just going to wander randomly around this flat world. But through machine learning, the dog eventually learned to bring the sheep into a group and put them into a little square area called the pen. How? Through again, it was learning through its own learning rules, its own behavioral rules, but it wasn't communicating with the sheep. It didn't become the god of the sheep and told them what to do. It was literally just the indirect observational interaction between the agents. It would say, okay, here's some agents. I know this pattern. I know what to do. And I do my next time step and I look at the agents again and I consult my rule book and I know what to do. And right. So it learned to corral the sheep, the simulated sheep. Then they put another sheepdog in. And the two sheepdogs, first of all, within the simulation, the dog could recognize sheep and dog, but that's pretty much all it could do. Within the simulation, the two dogs never communicated. It's not like, hey, you take the sheep on the left, none of that. The dog treated the other dog simply as an object in its environment. Again, only observational interaction, no direct interaction. And guess what? Those two dogs learned to coordinate their actions and corral the sheep. So that's pretty cool. Then they put in a wolf. So the idea behind the wolf was when the wolf comes in, the sheepdog has to make a decision. Do I continue to corral the sheep, or do I have to stop and defend the sheep from the wolf? Right? They kept adding complexity to this thing, right? So the idea was, okay, now you've got a sheepdog. Over time, it will learn to, however it learns, to defend against the wolf and still corral the sheep. But when you've got two dogs in there, now you've got a question. And this is where that was a long way to talk about heterogeneous behavior, but we get into heterogeneous behavior. You could develop a system where one of the dogs is always the anti-wolf guard dog, and one of the dogs is always the sheep herding dog, or one of the dogs is always the sheep herding dog, and one of them is always a sheep herding dog unless there's a wolf. In other words, you've got two different dogs here. They're heterogeneous in their behavior. Or you could have had it where both the dogs are the same, and one of them at some point will stop doing the sheep to go protect against to take care of the dog. They'll take care of the wolf. Now they're both the same. Now they're homogeneous in their behavior. And you can get into discussions as to what's the right way to go. Should you have homogeneous or heterogeneous behaviors in a system? That's a decision within a system that people may have to make. And it may be that this comes down to, if you think about skills, is it better to have a workforce where everybody has the same skill set, but maybe they're not great at any of them? Or is it better to have a workforce where you have specialists and they're really good at one or two skills, but they can't do any of the other skills very well at all? So what's better? Now, in the real world, we tend to have specialization, right? You guys are getting different degrees, specialization. But in some systems, you may have to say, okay, when I design this system, right up front, I need to make a decision. Should I have specialists or should I have generalists? Should I be heterogeneous or homogeneous in my agents? And if you're going to study that, one way to try to study that would be create some simulations and see what happens if you have specialists and generalists if you have heterogeneous or homogeneous agents. People who study this also study, again, in terms of skill set. If I have a service-based industry, so here I am, I've got, in the old days, people standing behind a counter, now they're sitting in a phone line probably somewhere. But people standing behind the counter and customers come in and they have service requests. Should you have broken it up where some people are going to handle certain kinds of service requests only? In other words, the people who are providing the service are heterogeneous. Or should you have it where people are, they can accept any task? And then you can try to study the throughput, right? The efficiency of the system. How many service requests can we respond to? People ask these kinds of questions. They study these things. Those are called queuing models. A queuing model is where people line up in a queue and then they get serviced. And the queuing model is trying to study how many people can you get through the queue? And then, you ask questions like, what's the maximum expected wait time? Right? What's the longest the queue will be, et cetera, et cetera. And these models can get, as you would expect, very complex. People study elevators. Right? Elevator studies are queuing model studies. Where should they? What's the best way to handle these things? Should I have all my elevators behave the same, or should I have some elevators do different things? So if we have I need to look at my I don't like these. I need to rewrite some of these notes. If we're looking in here for how to construct these models, if you can't describe the individual behavior, right, then I need to go back and look at that. I'm sorry. If the individual behavior is complex, agent-based systems can be good, but you're going to be focused more on the agent than you are going to be on the interactions, most likely. I need to go back and study this. I'm sorry. I need to read the Bonobo paper again. It's been a while. System correctness at agent level and aggregate level. Okay, yeah. So these are reasons again to employ the agent-based simulations and to focus on the agents. I'm not remembering, quite frankly, off the top of my head what I was getting at here with these short things. However, some of them I can see. Randomness applies to agent behavior. Yeah, that's a good thing. Agents are decision makers. As I said, if you have a decision maker who is deterministic, meaning it's always doing the same thing, then you tend not to have very interesting systems because they tend to do the exact same thing all the time. Same initial conditions, same output all the time. That tends not to be that helpful. System correctness is measurable at the agent level and the aggregate level. What that means is we're talking about validation and verification. So if you're saying, I can take this system and I want to compare it to a real world system, but I don't know how to do that at the aggregate system level. But I can do it at the agent level. In other words, I can say, oh, here's how a human being X tends to behave, and my agent actually does that. Oh, okay, that's a good argument to use agent-based systems, because what you're doing is you're modeling the thing that you know you can model correctly. And then you're going to get the aggregate level results. System is described more naturally the activities of the process output. Yeah, again, so if you have a system where you can describe the activities, in other words, do step 1, do step 2, do step 3, do step 4, again, that's an argument that you want to have an agent-based system, because that's the thing that's going to do those steps. Individual behavior is complex. Again, that's an argument for agent-based systems. It's all coming back to me now. Agent-based systems, because by complex, we mean that you can't just model it with a couple of, like in Boyd's was really stupid, simple individual models. By complex, we mean you can't just model it with a few simple rules. So again, embodying the complexity of a particular behavior within the agent is a good idea. And then the individual behavior cannot be described. Oh, that's the reverse of what I was saying earlier. So basically, if you have the aggregate rates, and then you can say, oh, what is this individual doing? Well, there's 10 of them, so it must be doing 1/10 of the aggregate. If you're in a system where that doesn't make any sense, then it makes sense not to focus on the aggregate rates and try to backtrack to what an individual is doing, but actually model the individual and then figure out what the aggregate is doing. Okay, that's plenty for today. I'm going to turn off the recording, and then I want to talk to you all about I'll go on one-to-one, talk about your reports. If you have anything at all in the draft, and I don't care how bad it is, I'll just take a quick look at it. If you don't, then let's talk about what ideas you have.